Hello. Temporal interaction networks are ubiquitous. Take yourself for example. When you purchase an item on an e-commerce platform, you create a directed edge indicating an interaction from yourself to the item. Each interaction is associated with a timestamp and a feature vector. For example, the amount you paid for the item. As time progresses, more user nodes, item nodes, and interaction edges are created in this temporal network. Such networks give an efficient framework to represent interactions in many domains, such as e-commerce, finance, education, healthcare, and social networks. Representation learning presents a powerful approach to model the dynamic evolution of users and items, where each user and item can be embedded in a Euclidean space, and their evolution can be modeled by an embedding trajectory in the space. These trajectories can be trained for downstream tasks such as recommendations and predictions. However, representation learning for temporal interaction networks poses three major challenges. First, the interest of users changes constantly over time, and therefore, updating its embeddings only when the user takes an action is not sufficient, as the embedding quickly becomes stale. Thus, making efficient recommendations requires us to predict the state of the users at any time in the future. Second, real-world networks have millions of nodes and edges, so the models have to be scalable. And third, to be practically useful in real systems, we need to generate recommendations in near constant time, irrespective of the number of candidate items in the dataset. Therefore, we create JODIE, a mutually coupled recurrent neural network model that learns to generate embedding trajectories of users and items from their interactions. JODIE trains two RNNs, one for users and another for items, which update the embedding of user and item using each other's embeddings. Notably, JODIE trains a projection operator that learns to accurately predict the embedding trajectory at any future time. JODIE can then use the future state of the user for downstream tasks. To make JODIE scalable to large networks, we develop a batching algorithm called tbatch. Tbatch creates a sequence of batches such that all the interactions in each batch can be processed in parallel, and processing the batches in sequential order maintains the temporal dependency of the network. This makes JODIE scalable to very large networks. In our experiments, we show that JODIE is highly efficient in both recommendation and prediction tasks. It performs 20% better than state-of-the-art algorithms in predicting future interactions, and 12% better in predicting the change in state of user, where we show that JODIE can predict when a student drops out of a MOOC course and when users turn malicious in online platforms. JODIE does all this while being 9 times faster in training than existing algorithms, and it creates near constant time recommendations. The code for JODIE algorithm is available on the project website. For details, please refer to the paper. Thank you for listening, and we hope to see you at the conference.